Okay, let's start. And I would like to make some comments before we start the lecture. A number of you have asked for a reference book. If there is any book that I believe is the best to use, it's not perfect, but the best better compared to what we had last year. It's this one, Elements of Electromagnetics by Matthew Sadiku. You can find it in the library. There are many old versions of it. This book is not new. You may find used versions on Amazon that you can purchase electronically for a very little money if you want, but it's up to you. If you want anything different, anything additional, I would go to this book. Now, for those of you who have access to last year's textbook, and sometimes those become available. Maybe you got one from a friend or something. Read it carefully because some of the notations are different. And so don't copy one by one, just read the approach the book is using. But pay attention to notation because notation, unfortunately, in a number of books, as you know, the fundamentals are about the same in notation, but when you go to derivative parameters who are not as, at the highest level of definition, but who are coming as derivatives and so forth, you will see that there are some different notations. Also, the previous books, for example, have the possibility of using bold letters and regular ones. And in some books, bold means vector. This means scalar, but it's difficult to write on the board. So what I'm using is this one as a vector because it's clear that it's a vector, and this one as scalar. But in last year's book by Ulabi, the bold ones are vectors. The other also thing is some books use these as the unit vector. I avoid that because sometimes as we write things on the board, you may see something like that, and then from far away you may think it's this. And the difference between a vector R and a unit vector is very high, so it's very large. So for me, what I have adopted is AR to be a unit vector, because you don't miss it. You understand whenever I show something like that is a unit vector. And this one is a vector. So this one, for example, can be this AR. So why do I say that? Because these are fundamental differences when you go from one book to another. So as you read from other books, make sure you understand their notations, and then you read, and then you learn from whatever else they have in there. Okay, so that would apply to other things. So read the notations carefully. What I have decided to do from now on, knowing that this book does not have many examples, I will solve examples. So I will solve an example, and then we'll do a conceptual question. But I will solve the example in detail first, and then we'll have the conceptual question. We also do examples in the problem-solving session because if we only do examples, an example may take a long time, and then we're not going to move through the material that we need. So I'm trying to somehow combine the problem-solving session with what we do in class to give you more examples and a better experience about the details. Okay, so you see here the summary. So I also outlined there what we're going to talk about. So in the summary, I wanted to remind you that we started magnetostatics by looking at a charge that moves with a velocity v in the presence of a magnetic field B. And then we ask the question, what happens to this charge? And of course, what happens is that there is a force that applies to this charge, which is equal to QV cross product with B. So if you want to see what happens to a charge in a magnetic field, then of course you will have to find that. Now, this applies, as you can see from here, if the B field changes, that implies that every section of the B field will exert a force, and then you will have eventually to integrate over that. But if the B field is uniform, all right, that in that case, you can easily use this formula and find what will be at this moment when the charge is here, this distance from the B field, what will be the force that applies to it. So that was the fundamental equation. And then through that, we defined B as the magnetic flux density, which is equal to m mu h, where so B, magnetic flux density, vector, mu is called the magnetic permeability. For us, for now, is a scalar. Permeability. H is the magnetic field intensity, vector. All right, V, of course, is velocity, the velocity of the charge. Now, unless the material that you are using is a magnetic material, all of the dielectric materials have a mu, so for all dielectrics have a mu which is equal to mu of free space. And that is equal to 4 pi 10 to minus 7 Henry per meter. Right? Do you remember how much was epsilon naught? The electric permittivity was 8.85 10 to minus 12 farads per meter. Now, I want you to observe something because it will be useful later. Look at the units of epsilon naught. So what does that remind you? Capacitance. And in fact, capacitance per unit length. So E naught, in reality, is a parameter, we defined it, but is a form of a capacitance, and is called a generic capacitance or intrinsic capacitance. Sometimes in some publications, you will see that as the intrinsic capacitance of the medium. But in reality, is a constant and it has the form of capacitance. Later on, it's going to help you to remember that, because later on, we're going to see that coming back. How about this mu? Inductance per unit length. Intrinsic, sometimes known as intrinsic inductance per unit length. All right, so I want you to just look at that. Okay, now let's try to go from charges to currents and see what if I, instead of having a charge in a magnetic field, now I have a magnetic field. Let's assume that the magnetic field is uniform. All right, everywhere. And I have inside that magnetic field a wire. And that wire in the beginning has no, that's a problem, all right? So let's try to look at this problem, and we're going to introduce a relationship between then the current, a steady current, and a magnetic field. Okay, let's assume now that this is a wire, but has no current that flows through. If nothing happens here on this wire, if there's no current, that means that there are no charges that go through the wire, right? And so the wire is going to remain like that. And then at time t equals 0, I have a current that flows through the wire. The question is, what is going to happen to the wire? It's going to be in the same position. Let's assume it's a very flexible wire. When is going to happen to it? When you have currents in the wire, you have what? Moving charges. When you have moving charges, then and they are inside the magnetic field, then you have what? A force that applies. But before we find exactly what force is going to apply on this wire, we need to move our relationship that we had here, all right, for the force. Where is that? Here. We need to rewrite it in the form of a current and the magnetic field B. Okay. So how are we going to do that? I can erase this. And I don't know, I have to tell you, I've done everything with this one, and I don't know why it still goes blank. Okay, so here, when a charge moves, let's assume that we have a bank of charges, Q. And these, there are different point charges. And they are steady. They don't move. Q1, Q2. Let's assume that these were all of our charges, all of them inside the volume B. So there is a total charge Q inside the volume B. And then all of a sudden, this charge, Q, little q, starts moving out with a velocity v. That what happens to this total? Let's assume that all of them are positive charges, all right? And this one, all of a sudden, we do something to it, and it starts moving with a velocity v. What happens to this total charge? It decreases because it's all positive. So one of them leaves. So practically, this charge decreases. In fact, or this one, rather, let me write it. Q then goes down, which means if the Q goes down when that starts moving, it leaves the volume, V, down. What does that mean about, what does it mean, what does it happen to its derivative? It's negative. And what else do we know? That when that happens, then I have a current, all right? Because we know that the negative of the derivative of Q over time is what? We defined it before. Is the current. But negative here and negative there, I could say that if I take this, the absolute value of that change, that gives me the current that is created. Just to avoid negative and positives, which in fact the negative and positives will only impact the direction of the current. In this particular case, because this is positive charges, this is a positive, we have defined the direction of the current as the direction of the positive charge, okay? Not the direction of the electrons, not the direction of a negative charge, but the direction of a positive charge. That's how we have the convention we have used. All right, so that tells us that this one is really a current. Okay, so if this is a current, then I go, let's assume that I have this Q, or this, I rewrite this expression for this little Q here. And now this Q, which is a small value, it goes inside the magnetic field. All right, I have this magnetic field here. Okay, I'm going to erase that. So since I have this magnetic field, this one, this charge Q, which is a small charge, is going to feel a small force. So I put it here like that. And then this small force is going to be nothing else but QV cross B, where now V is nothing else but dl dt. All right? This is velocity, which means, and this is length, which means that Q dl dt here is exactly VQ. That is QV, rather. And because I can rewrite this, because this is a very small change of the volume, I can rewrite this as dq because the volume changed by this. All right, the change in the change in the charge in the volume, it was like the dq in the charge over time t. It was nothing else but q. That was exactly what left the volume. All right. So the small change in the total charge, it was exactly equal to that left the volume. And then I can rewrite this as dq dl over dt. And this one is equal to qv. But this is current. So since I'm talking about positive charges, of course I don't use a negative sign. dl equals qv. See how I went? I mean, I did it on a very simplistic model. So you see that really that this small qv, small charge, small change in a big charge, all right, this q that left the volume, when it started going with the velocity v, it's nothing else, really. This product qv is nothing else but this product here. And of course, we need to have this one here for the direction. Since there is a direction and not just the distance, then we have a vector. All right? So we have that. Do you have any questions about how we derive this? Okay. If we now have this in place, I can rewrite this one. How I can rewrite this? I will rewrite it up here. Equals I dl cross b, dl cross b, nothing else I have. All right, so practically I have now a force that is exerted on a small current, all right, by a magnetic field, B. Now, this is very useful because if you have a current like this and then it's of a distance L, you can integrate that practically and you can get rid of the derivatives. But I will use it like this because it's a more general form. Let's take this one here. That tells us that if we have this section of the current, okay, and this section of the current here, this small, is going to be what? I dl, okay? And dl is going to have a vector because the current has a direction. And let's assume that we are using here a coordinate system. So we have x, y, and then z. Now, what is dl? dl is along the x direction. So it's I dl along the x direction. Okay? What is b? B is along what direction? Negative z. Negative z. So B is like B, but negative z direction. The positive z is like that, coming out of the wall towards you. All right. Now, if I take this equation and I go behind it, below it, and write, see what happens, I would like to see what is this force on this small infinitesimal element, and I will see that it's going to be I said is I dl ax, excuse me, ax cross b along minus a z. How much is that? Is take all of the scalars up front. How much is that? Exactly. That's AY. AY. So I found that something very interesting, that if the current flows like that, there is going to be a force only on this one that goes like this. So there is, since there is not just this small current here, but the current extends from here to here, there is going to be a force that is going to move it here, like this. And if it's a force that moves it like that, and these are steady, these are 2 points that they are anchored, cannot move, how is this going to flex? It's gonna, we are going to see a deflection of this wire like this. Okay? Because the force tries to move it here, and of course, the force at some point is going to be neutralized by the mechanical forces that are forcing the wire to come this way, the stress that is exerted on this. Eventually, it's going to pull it back and then stabilizes at this point. Okay? If the current was going the opposite direction, so the current was going like that, what would happen? If it goes, if only the direction of the current change, I mean, it becomes from positive x to negative x, your force is going to go along the negative y. There's nothing else that is going to change that, all right? The sign only. So without going through this, I can tell that the force right now is going to go like that. And it's going to flex this like this. And it's going to stabilize at some point. So all of this, we were able to make that decision that it went this way using this formula. Any questions on this? All right. So now we're going to move to Biot-Savart Law. There was, we're going to come back to this for other, maybe then I need to ask you another question since we looked at that. Let's assume now that I have this current. I take the same current, but now my magnetic field, it goes along the negative z. So let's assume that this is, if my z goes like that, or in fact, no, I change my field, and my B field goes like this. All right, that's B. And my current goes like that. What is going to happen to the wire? What is the cross product of two vectors which are parallel to each other? 0. So F here, or dF, or F if you like, is 0. So there's not going to be any force that is exerted on this. Okay? All right, so these are the 3 cases. let us now go and introduce Biot-Savart. Oops. Okay. Can you see when I write with a chalk on the board? Okay. So we'll just define it. And I will define Biot-Savart for line currents. So I mean for a wire, if you like, or a line current. Line current. Okay? So for example, the wire is that wire. Wire goes like this, for example. Like this, okay? All right, so that says the following, that if I have a current that flows, let me do this current. This is an infinite wire. We have that B is created, so this current I creates a magnetic field, all right? And this field B is given by mu naught over 4 pi, the integral along this line, I dl cross R. And in fact, maybe I will make it not infinite, because even if it does not exist, you know, I have tell you, in reality, you cannot have a section of a current. It has to be given here by something. But let's assume for now that we have a section of the current. This is for the sake of introducing the formula. We could have a section of charge, because charges can be placed somewhere, but you cannot have a section of a current because charges flow. So the charges will flow from here somewhere, all right? It could be something like that, for example, going somewhere. But now we are going to have a section, A, B. It's a theoretical, not practical. All right. Or, if we remember from electrostatics, this one can be written, and this will be obviously from A to B, all right? A to B here. I dl cross A sub r, which is the unit vector, and I will explain what those are, square. Where now I'm calculating, due to this current from A to B, I'm calculating the magnetic field here, all right? And what is R? If dl is somewhere here, and that's my dl, then the dl with the direction of the current is a vector, all right? So it's going to go like this. Then it's the distance from the center of that to this point B. And of course, it's going to have this direction because it's a field that is excited by this current. So it's going to be R. This is your R. Okay? So when we have a line current from A to B, then a infinitesimally small section of this current will create a infinitesimally small section of B, a part of a magnetic field. But then if you integrate from A to B, then you're going to find the total magnetic field that is excited by this current. And that is a formula that we will use to calculate the magnetic fields in a distance from a current that generates it. All right? Now, before we go to something more complex, I would like to introduce another law, which is also very useful. And that is going to be Amperes Law. So we're going to introduce the two, and then we're going to use them depending on the problem, all right? Sometimes it's easier to use Amperes Law to find a magnetic field. Sometimes it's easier to use this one to find a magnetic field. But both should give the same result, all right? Okay, now Amperes Law. Do you see if I write here on this, or is it too sideways? Maybe I'll write it here, and then okay, I write it down here. So Amperes Law, can you see down here? Yes? Amperes Law okay, there are two ways of writing Amperes Law, in the differential form and in the integral form. I'll write the differential form that says that the curl, if there is an electric field, field density, electric current density, which generates a magnetic field B, then the relationship between this current density and the magnetic field is given by this, if it is in free space. That's Amperes Law. So there are two different relationships now we have written down that relate B, the magnetic field that is generated by a current, I. And of course here it's in integral form. Here is Amperes Law in the differential form, but I will also write it in integral form. So we'll have two different integral expressions that will give us a relationship between the current and the magnetic field it generates. And the integral form, do you remember, is coming out of the differential form using Stokes Theorem. You remember when we spoke about Stokes Theorem once? We spoke about the divergence theorem, all right? And then we spoke about Stokes Theorem. So what Stokes Theorem does is it tells us if we take this and integrate over a surface, so this is a current density. And currents, let me explain to you also. Currents flow like that. Charges are like this, all right, in unique positions in space. A current cannot have a position like that. So a current density in the most general form will be amps per meter squared. You cannot have a current density in amps per meter cube. But we could have a charge density in coulombs per meter cube, because charges are at points. Currents flow along lines, okay? So if we have a current like this, and it all flows through this wire, all right? Then the total current that flows through this wire is how much? The integral of the current density, J, times the area. Okay, that's the total current. And therefore, I will go here and integrate both parts over the area of this wire. Okay? And that's the most general way of doing it because I don't know whether this current density is uniform. Now, if I go to the other side and I integrate this cross product over the same surface S, Stokes theorem, so here Stokes, tells me that this one can be simplified to what? To a line integral of B dot dl, which is then equal to the surface integral of J dot ds. So practically, this is the simplest form of the of Amperes law, where S is this and C is this. And if S has this direction, this is the vector for the surface N, then you need to use the right-hand rule. C is going to go like this, okay? So if this is N, your C direction is this. You have to use the right-hand rule to find the direction of C, because these directions are important, okay? So we are going to use now these ones to solve problems, solve some examples. But before I start with the examples, do you have any questions? Yes? C is this, the line that encloses the surface. Yes, in this case, the perimeter of the wire. All right, so let us solve some problems now. We'll try to solve a simple problem first, which you probably will use quite a bit, and that is the magnetic field from an infinite wire. All right, let's try to do that and see which of the formulas we're going to use. Okay, so I have an infinite wire. In fact, I will bring this here and write it so I can free up some space there. In fact, this is also 1 over mu naught. So I will write it here again. 1 over mu naught, line integral B dot dl equals the surface integral on the cross section of the current J dot ds. Okay, so now I can do that. And let us try to solve the problem of an infinite wire. All right, infinite. And then it goes a current I. Now, which of the two am I going to use? What do you think? Can I use this one? If I were to use this one, what would I have to put for A? Minus infinity, and then this one plus infinity. Okay, so I would say, before I go there, let me see whether I can use this one. What does that say? We started with a wire that had a thickness. All right, that's where I started before. And I selected as a surface the cross section of the wire. did I have really to force myself to use only the cross-section of the wire? Could I use a different surface? I mean, does Stokes' theorem force me to use only the cross-section of the wire? No. All right? Stokes' theorem is very general. It applies on any vector. If this is vector C, Stokes' theorem says that the surface integral on any surface, any of these, is the line integral, is the line integral of B dot dl on the line that encloses the surface. So if my surface is like this is S, and if the S has this vector outwards, all right, towards me, then that's C. But I could select any. Okay, so what am I going to do here? So I'm going to go away from Biot-Savart and say, let me try to use this one, looks simpler. But I'm going to use as a surface a circle. That's my surface, S. And let's assume this surface, if this is my point, and I want to find the value of B at this point, and I go to this surface, all right? That's surface S. What is the direction of this surface? I take as the direction this one. And, okay? What will be the direction of the line that encloses the surface? This, C. So I could use this one and then go here and say, okay, now I'm going to write this as follows. 1 over mu naught, so Amperes law. Amperes. Okay, 1 over mu naught, and then now it's the closed line integral around this circle, because this has a radius of r. And therefore, I write this, which is B dot dl, okay? And then, how much is this one through the surface? This is the surface. This is my current. And the current here, what is it, the value of the current, or the J? It's because it's a line current, okay? Practically, this is I along this direction, okay? And then we have already called this direction N. That's the same direction of the surface. It does not have to be the same. It could be something different. But now it happens to be that. And in here, I would have the surface integral of I n dot ds. How much, what is, in other, maybe not how much, but what is, how can I write this ds? This ds is like n ds, okay? You follow me? All right, so these two give nothing else but I. Okay? Yes? Could you speak louder? Oh, this is the direction of this current. So in this form, we have a current density. Here, the current, in reality, this is the density because it goes, it's a line, it's one line, there is nothing else around it, so I can write it like this. And that is the direction of the current. It goes along this direction, okay? I have selected N to be like this. It happens to be along that direction. So it gave me I. All right, so practically, I'm happy with this because I can go up here, all right, and I'm going to have B dot dl equals mu naught I. Now, let's think about this problem. This problem is one wire, a straight line that goes from minus infinity to plus infinity. If I were in the cylindrical coordinate system, that will be z. Okay? In the cylindrical coordinate system, that will be z. In reality, z, the direction of n, is nothing else but a sub z. All right? If I define my Cartesian, my cylindrical coordinate system so that z aligns with the direction of the current and is therefore along the axis. Because there is nothing else around it, what do you think is going to happen to the magnetic field around this current? It's going to vary with phi. Is it going to vary? How is it going to vary? It's going to only vary radially, but not with phi. Because if I am here along this, if I am here on this circle or here, I will see the same thing. All right? There is no reason not to see the same thing because it has a cylindrical symmetry. So that says to me that B along this line is constant. This is a circle. Remember that. Okay? So B along C is a constant, which then makes me rewrite this one to the following. C, B naught, okay, B, let's keep it B. And then I have the direction of B, let me call it, all right. Before we go there, one more thing. B is that product with DL. So we found that B, first of all, is constant in value. But how about the direction? B is in fact a dot product with DL, and DL is a small section on this circle. And let me take this circle to show you exactly how we're going to integrate. So what happens on this circle, this is in the circle that I have here. All right, this is C. Now, this one is Z. This is Z. And on this one, in cylindrical coordinates, we have A sub R, A sub phi, and A sub Z. Sometimes you will see it as R, phi, and Z, just for those who have seen that. I'm not using those. I'm using these. All right? That's how it is defined in a positive cylindrical coordinate system. Okay? So if I take this small DL here is what? We write it, as you know, this is d phi, this is dl, and the direction of L is along the phi direction. All right? It goes like that, tangential. So dl is nothing else but a scalar multiplied by this vector. How much is this area dl? If this is d phi and this is r, then dl is r d phi. Okay? Do you remember those things from the long past? Okay, from the long past. Just I do that slowly so I can remind you. dl is rho d phi for very small values of L, of course, for differential L and differential phi. Otherwise, does not apply for large values of L and phi, obviously, all right? And then I can rewrite this as R d phi A sub phi. Okay, now let me, since I've done this, let me go and work on this one. So now this one becomes the integral then, since it becomes d phi, it goes from 0 to 2 pi. All right, that's the C of B naught R d phi, since it's constant, all right, R d phi A sub phi, in fact, that, well, excuse me, so I should probably do that. B naught A sub phi dot R d phi A sub phi, which is dl. So the inner product between this I sub phi and this is 1, all right? And there, this is going to give, so you see that clearly? Let me write it clearly so you can see it, because I don't know whether you see that well. So this is going to be phi, only this component of B exists, you know, in this inner product. So it's going to be R d phi A sub phi. This one and this one, inner product, gives 1. So practically we have, this is constant. We take it up front. And then what we have, this is a constant too, because we are on circle who has radius r. So this is a constant. And then we have only from 0 to 2 pi d phi. All right? And that is equal to mu naught I. So how much is this one? This one. This integral from 0 to 2 pi d phi. 2 pi. Okay? So practically, we have here 2 pi. And therefore, B is nothing, B naught is mu naught I over 2 pi r. Okay? Which then means I found my B. B is mu naught I 2 pi r A sub phi. So I found the magnetic field that is produced by an infinite wire. And that's very useful to keep it in mind. So it changes as 1 over r. Do you remember an equivalent expression from electrostatics? The electric field that is generated by an infinite line charge. Remember that? It changes as 1 over r. 1 over r. So if your source is an infinite line charge, it generates an electric field which changes as 1 over r. If it's a current line, infinite line, current line, it generates a magnetic field that changes as 1 over r. So you need to remember that. Okay, any questions so far? What time is it? Okay, let me see. Questions? Yes?
Yeah, how does the magnetic field have that direction, A sub phi?
Okay. There, it shows that because of the inner product, and the inner product here only allows the A sub phi to exist, from here we find that the A sub phi, the magnetic field, what the current generates is only a magnetic field with one component. It does not generate other components. That's what that tells you. Because the other components do not, if you had other components here, they will go, any contribution will go to 0, which means that your electric field does not generate other components. All right, so that's because of the inner product here. And that applies only for a line, an infinite line charge. That's not true for everything, all right? When you have a circular wire, where the current flows like this, then that assumption is not true. It only applies that the magnetic field goes along the phi direction on a current. It only applies for this one. And as a matter of fact, it shows that you can use the right-hand rule, that if the direction of the current is like this, the direction of B is going to be like that. And B is going to be given by this. All right? Okay. Let me see. Now, I have, what do I have? Okay. Let me then ask you the following. I'll set up a problem. We'll discuss it, and then I will ask you to solve a top hat, a question. But we are going to discuss the problem first. Okay, what did we learn early, when we got early, meaning when we got into magnetostatics? The first formula that we put down was which one? The magnetic force. And was what? That the magnetic force was what? QV cross B. So what we've learned is that if there is a magnetic field, B, then, and if there is a charge Q that goes with the velocity V, the force that applies on this charge is given by that. Okay? Now, what did we just found? We found that if we have a current I that generates a magnetic field B, which is circular, all right? The magnetic field B goes like that. All right? It goes out. And a magnetic field B here goes along the phi direction. So how do you show the phi direction? Let me show it down here. It goes like this direction. All right? This is the phi direction. That's your B here. Here it's going to go like inside the wall, and then it's going to go, it's like circulating around, all right? That's the phi direction. That's your B. That's how the B goes, all right? We said that's what we found. Is that right? And we found it's constant from an infinite current. Okay. That means that now if I have a current like this, I, and I bring a Q here, that goes with the velocity V, what is going to happen to this Q? Yes?
For the direction of B, you think it's just drawing coming out of the board, right? Next to the wire?
Here.
Yes, the dot is recognized as coming out of your board.
So here, on the same plane,
Yeah.
it's going to go inside, because it's like this.
Oh, on one side, yeah. And then out on the left.
Yeah, and then here like this. Okay. All right, what is going to happen to this Q? Because there is a current, there is a B. What happens if there is a B? There is a magnetic force on the charge. How do you find this magnetic force? By taking the cross product between the velocity and the direction. This is so assume that Q is on the board. My Q is on the board. At this point, how is it going to be the direction? So it's on the same plane with I. That's what I'm saying. My I is on the board. Q is on the board. All right? What is the direction of the magnetic field at the position where Q is? Okay, what is going to happen? You remember I said there are lines like this. All of the magnetic field goes like that around the wire. So here there is going to be a magnetic field that is going to be constant along the circle that goes through the point, and it's going to be along the phi direction. So how is this going to, what kind of direction the magnetic field is going to have here? All right? So we know the direction of the magnetic field B. We know the direction of V. And the cross product of the two is going to give a phi sub m. Is that understood? OK. Now, I would like you to solve a problem. Not exactly to find the exact force, but to find if there is a force, all right, for different positions of the charge. Have you understood this problem before? Did you understand the discussion we had before we go to top hat? Yes?
Velocity is also blue, and that means no.
Yes. So that's what you will have to figure out. All right, so let me do this now. What happened? Ah. Okay. That's the problem. And I will leave you, I want you to solve it, so I'm not going to put too much pressure on you in terms of time, but it will be nice if we can get it done in about 5 to 6 minutes, but we'll see how it goes. I want you to think on the basis of what we discussed and to ask the question. And the question is, which of the cases will give a zero force? All right, so I'm going to assign it now, okay? And then you should be ready to start working on it. And I will remove it from here so I can see what is happening while you're doing it. Okay. Everybody has entered? I think probably the answer is yes. On the basis of what I see. That's what I'm saying. I can see how many of you, so I can see how many of you have responded already from here. So, okay. Okay, I will unassign it and show you what you get. Okay, well, let me see. Okay, that's what you got, which is B. B. All right? As it should have been. Okay. Let's try to solve another problem now on the board. And then we'll do one more before we go. Yeah. Okay. We found the magnetic field due to an infinite wire. Now we are going to find the magnetic field that is produced by a circular wire. All right, the current that flows on a circle, perimetry of a circle. All right. Do you know why this problem is important? The one that the magnetic field, the current flows like that? Yeah, for a lot of things and for inductors. Inductors in general, of course, motors, everything, all right? That's how we have coils. Practically, they are all round. So this is a fundamental problem. Okay, I raised it so I can, let's assume that this is a cylindrical coordinate system. This is Z. And we have the current that flows on this, around this circle, I. And now we want to find B. And we want to find B, just to simplify things, along this axis. On the Z-axis, not just anywhere else, but on this one. So we are looking at this point P. And we would P point. And we would like to find the magnetic field there. that is introduced by this wire. Okay, what we do is that we take a short section. Now, in this case, we cannot use the Amperes Law. It's not going to get us anywhere. What we want to use here is Biot-Savart Law. All right, so according to Biot-Savart, remember here we said that B equals let me write it here, make sure. Mu naught over 4 pi, a path L, I, dl cross R third amplitude of R to the third power. All right, so we are now, see, we need to find a small section of this current. So dl is here, dl. This is dl. The current flows like this. As I did before, we are going to write dl as dl a sub phi. It goes along, of course, the phi direction. And dl is what? If this is, the radius is a, what radius a, then is a d phi. All right? So, R, let's find, this is d phi. R is the vector that goes from the center of this small element to this point here. So R goes like this. And R, let's look at, we found how to write this vector. All right, so let me write here. So we found the dl, because we have to plug in the relationship. This is along the phi direction and has radius a d phi as a value. All right? Now let's write R. R has how many components in the cylindrical coordinate system? 2. Which ones? Exactly, has R and Z. All right, because the way it is, there is no phi component to R, to this. It is connected to one point on the axis, on the z-axis, from one point on this circle. So there is no phi component in there. So R is going to have a component along the R direction and a component along the z direction. But here, according to that, what is the component along the R direction? A, the radius, but in fact, R has this component. I don't have other colors, I'm sorry, in the chalk, but it has this component and this component, all right? R has this and this, the two components. This component is A, but is opposite to the AR, all right, to the direction of the cylindrical coordinate system. This is the vector, the unit vector along the radial direction. So R is going to be A minus A sub R, to take into account the negative, all right, direction of this component of R in relation to the unit vector along the radial direction. And then it has the Z, because this is Z, all right? In this point P here has 0, 0, Z. 0, coordinate along the r, 0 coordinate along the phi, and z coordinate along the z. That's your point. And therefore, this is going to be written like this. Let me put this one. Okay? So now, I have to start plugging in there. Let me do the top one. I will do step by step. So B is going to be mu naught over 4 pi. That is going to be along the direction of the current, which is what in reality is a closed path, all right? Is this path, the original L we had here, because our current goes along the circle. So it's this C. And then we are going to have I. For dl, we have A d phi, and then we have A sub phi. And now we go to R, cross section, cross product, minus A alpha, or A, unit vector along the radial direction, plus Z, unit vector along the Z direction. Okay? So, what, and then divide it by, I will put this for now. I will put to the third power for now, and then we'll come to this next. But I'm gonna deal with the numerator. All right. So let's take all of the constants out. So in fact, only these ones, we'll move them out of the integral. So I will put them here. Okay? And then I will remove them from there. But I have to leave d sub phi here. And then I have to perform this. So let me do here. A sub phi cross A sub r, what is it? One. They're not the same. A sub phi and this is A sub r. This is cross product. How much is that? Plus or minus z? It goes like that. A sub r, r, phi, z. In the system that is positively. The cross product between these two gives that. The cross product between these two gives this. The cross product between these two, this gives this. So the cross product between r and phi will give z. But if it was this way, if it was to be the opposite way, will give minus z. Okay? So it's minus z. And then we have A sub phi cross A sub z. How much this is going to be? Okay. What I want you to do is to practice on this. Practice, practice, practice. Put it, you know how you practice it? Very simple. Put a list on a page of all of these different, and then try to solve it. Because it's only practice, all right? This is practice. If it takes you a lot of time to find that, then you're not going to have time to do what is more important. So we go here, and we have mu sub naught I A over 4 pi. I will still keep this, and then I will deal with that next. And then I have d sub phi, d phi. And then the first part, minus here and minus here, gives me plus A and A what? A Z. And then this gives me plus Z A sub r. Okay? So B has two components. Now I can write them. There is a Z component and an R component, okay, right here. So we are looking at that point. So if I go and look at this point, I find that B here has two components. Has one Z component and one R component. Okay? Here is the B sub Z. This is B sub R. So here I have mu naught IA over 4 pi. And then I will have, this is along the line, all right, of d phi. This is going to be from 0 to 2 pi practically, 0 to 2 pi d phi. And then I will have, this is 2 pi. And then I will have AZ plus ZAR. Okay, so this makes 2 pi. And then practically I have here mu naught IA over 2. And then, I'm sorry, I forgot that one, which I still need to have. Okay? So, let me write now the final form for B. The final form for B then is two components. We said A sub R and A sub Z. All right, now let me see one thing here. The before we integrate around the whole circle and then find that, all right, as we are here, so let's keep that for a moment here. If we are at this point and this small section creates this A sub R, all right, which goes, in fact, this A sub R is going to go like this along this direction, all right, it's going to be parallel to this. If I go to the other side of the circle and have this section, this current, going like this, what is this going to create here? It's going to create the same kind of B along the same direction, but it's going to have a similar B, but the A sub R is going to be along the opposite direction because the current flows like this here and flows like this here. So what is going to happen when you integrate through the whole thing, that the R components will cancel out. So practically there is only a Z component, all right, here. This is only true for the axis. It does not apply to any other point. So on the axis, B sub Z will have only a Z component. And this one, from those expressions, it will be in the following form. Mu naught I A squared 2, and then you're going to have 1 over R becomes A squared plus Z squared 3 over 2, because they here, for that reason. This one is nothing else but the square root of A squared plus Z squared. Okay? So this you can write it as A squared plus Z squared to 1 over half, to a half, 1 over 2. And therefore with 3 that we have there, it becomes like that. So this is the field that is generated, all right? And this is along the z direction, A sub z. This is the field that is generated by a circular, by a loop. We call it loop. By a current, all right, by a loop. When you say I have a loop, that means you have a loop of current, nothing else, obviously. So it's generated by a loop, and then it has a magnetic field along the z direction. All right? Now, what would happen if I would go there and I have another like this, but with an opposite direction of the current? What would only be different in this case? Assume that the radius are the same. Only the direction of B will be different. The direction of B at this point will be like this, because the direction of the current is different, that's all. Everything else is going to be the same, all right? Got that? Okay. Any questions so far? Let's solve then on this another simple problem. All right, it's kind of exactly on this topic. What happened here? There. Okay. Let's go to the next one. Okay. This is the question. It gives you, let's talk about that problem. It gives you a current that is closed, of course, on a closed path, but it's looking kind of like this. It goes around, it comes in like this, goes around, comes in like this, and then goes like that. So the current goes, let me see here, it goes like this, goes like this, like this, like this, and then goes around and continues, okay? And then it says, at the center, if you look at the center of the circle, at the center, all right? You remember we had that one circle here, and we looked up there, but if you look at the center of this circle, all right, what we found, I will write it for you, at the center where z is 0, what we found was that B was mu naught I 2a, all right? That's what we found for that. The previous expression I developed on the board, if you put a z equals 0 on that expression, what you really get is this. So if you have a current that flows like that, at this point, which is at the center of the loop, this is the value of B. All right. So now here, it asks you to select which direction the field will be, either directed into the plane of the drawing, out of the plane, whether it lies in the plane of the drawing is 0 or something else. All right, so I will assign it to you. You got everything that you need. And then please go ahead to solve it. And I will remove it from here so you are not influenced by what you see. Let's try to solve it in about 5 minutes. Are you still working? Okay. So then 1 more minute. Okay, are we ready? Everybody's in? Okay, I'll unassign it. And we'll talk about that. Okay, that one. That is the correct answer. Why is that? All right, so when the current is like this, okay, what we found is when the current is like this, we found that the magnetic field, okay, goes upwards here. When the current goes like this, well, when the current will go like this, it's going to go the other direction. So when the current goes like that, B goes like this. Okay, so here you have the current that goes like this. So B is going to go from this one outwards. Okay, so if this is I1 and this is I2, and then assume that Z is coming out of the board. All right, so I1 is going to create a B1, which is along which direction? Positive Z. All right. I2 goes the opposite direction. So I2 will create a B2 that goes along the negative Z. Now, how much are the B1 and the B2? B1, according to the formula that we derived, was nu I 2A, 2A, along the positive Z. And then B2, so A, how much it says? A is 2A, excuse me, because it's this, so 4A here. And the inner, so this is 2A, and this is A. And the other one would be mu naught I 2A. This goes along the negative Z, this goes along the positive Z, all right? So the sum of the two will be B, which is positive this, negative this, mu naught I over 4A minus mu naught I over 2A. And that's going inside the board. That's the correct answer. Okay? So what I would like to ask you is that to go through these problems yourselves, and try to go with try yourselves to go through the conceptual questions, the ones that we have, the material we have covered. But two things that I need to tell you. So for the midterm, I will give you a list of problems without their solutions. I will give you a list of problems that you could solve. All right? And from these problems, for practice, some of them will be very similar to what we've done. Some will be some variations of what we've done. And for practice, I will give those to you like a week before the midterm, and then you can ask me questions during office hours. You can ask the TAs and the whole thing. That's the midterm. On starting tomorrow, you can pick up during office hours from the TAs your quizzes, or you can pick them here on Monday. And on Monday, we'll talk about how we've been doing so far in the class. I will collect all of the points and see what we are doing as a group. Okay? Thank you.